Let's talk about mass. It sounds so simple, right? It's a word we use every day. But what if I told you it's one of the biggest, most fascinating mysteries in the entire universe? So let's really get into it. What exactly is mass?
So, what is mass? I mean, you think you know. It's how heavy something is, right? How much stuff is packed inside an object. And yeah, you're not wrong, but that's only a tiny part of the picture. The real story, the one physics tells, oh, it's way, way weirder and a lot more interesting. All right, so let's start peeling back the layers on this deceptively simple question. Because, it's not just about weight, it's about so much more.
So get this. Classical physics can't even agree on one single definition of mass. It actually gives us two. On one hand, you've got gravitational mass. That's all about how gravity pulls on you. It's what your bathroom scale measures, it's what gives you your weight. But then there's inertial mass. This has nothing to do with gravity. Zero. This is about how stubborn an object is. Its resistance to being pushed around. It's the reason it's so much harder to shove a car than a bike, even if you were floating in deep space where there's no weight at all.
And right here, this is where the real mystery kicks in. You've got these two totally different ideas, right? One is about gravity pulling. The other is about pushing. They seem completely unrelated. So why do they always have the exact same value? I mean, think about it. If something is twice as heavy, it's also exactly twice as hard to get moving. Every single experiment ever done has confirmed this. Is that just some crazy cosmic coincidence?
Well, if there's one person who absolutely did not believe in cosmic coincidences, it was Albert Einstein. He looked at that perfect match and thought, no way, that's not an accident, that's a clue, a really, really big one.
And to chase down that clue, he came up with one of the most brilliant thought experiments in all of history. Picture this. You wake up inside a sealed elevator. No windows, nothing. You feel your feet planted firmly on the floor. Now the question is, where are you? Are you just sitting still on the surface of the Earth, feeling the normal pull of gravity? Or are you actually floating in deep space, inside a rocket that's accelerating upwards, pushing that floor into your feet? The wild part? There is absolutely no experiment you could do, no test you could run to tell the difference. None. The feeling is identical.
And that incredible realization? That's called the equivalence principle. It's this core idea that the pull of gravity and the feeling of acceleration are, well, fundamentally the same thing. They're indistinguishable. And from this one simple, beautiful idea, Einstein built his entire theory of general relativity.
But Einstein wasn't done. He had another huge piece of the puzzle up his sleeve. And yeah, you've definitely seen this one before. E = mc squared.
So what does this famous equation actually mean? Well, it means that mass and energy are basically two forms of the same thing. They're interchangeable. And this implies that any form of energy, whether it's the energy of motion, chemical energy in a battery, or even just pure light, it all adds to a system's total mass. So yeah, a fully charged battery is actually a tiny, tiny bit heavier than a dead one. It even means that light itself, which has no mass, still has to behave like it does because it carries energy.
And believe it or not, this isn't just a theory. We've actually seen it happen. Back in 1919, astronomers were watching a solar eclipse, and they noticed something impossible. There was a star that should have been completely hidden behind the sun, but they could see it. How? Well, the sun's enormous gravity was literally bending the fabric of space, and the starlight was following that curve, traveling around the sun to reach our telescopes. It was the ultimate proof. Energy, in this case light, is absolutely affected by gravity, just like mass is.
Okay, so sounds like Einstein's got this all figured out, right? Mass is energy. Simple. Well, not so fast. Because the other great pillar of modern physics, the Standard Model, has a completely different story to tell, an entirely different explanation for where mass comes from.
The Standard Model says, imagine there's this invisible energy field that fills up every single nook and cranny of the universe. It's everywhere. We call it the Higgs field. And the theory goes that fundamental particles aren't just born with inertial mass. Nope. They get it by slogging through this field.
The best way to think about it, really, is like this. The Higgs field is a kind of cosmic molasses. It's everywhere. Now, some particles, when they try to move through it, they feel a ton of drag, like they're wading through thick syrup. We see that drag as having a lot of inertial mass. Other particles just zip right through with almost no interaction, so they have very little mass. And some, like photons, particles of light, they don't interact with the molasses at all. They just fly right through, which is why they have zero mass. And boom! There it is, the central conflict. We have general relativity, an incredibly successful theory, telling us that mass comes from energy, and then we have the Standard Model, an equally successful theory, telling us that inertial mass comes from this Higgs field. They can't both be right about this, so what gives? Let's really dig into just how deep this conflict goes with another great thought experiment. Okay, follow me on this one. We take a box, a special box with perfectly mirrored walls inside. The box itself has an inertial mass of 1 kilogram. Now we start filling it with light, just pure energy. We keep pumping light in until the energy inside is equivalent to 10 kilograms of mass. Simple question. What is the total inertial mass of the box now?
Okay, so let's see what our two rock-solid theories predict. Einstein's general relativity is pretty straightforward. Energy is mass. So you take the 1 kilogram from the box, add the 10 kilograms of energy from the light, and you get a total inertial mass of 11 kilograms. Simple. But now look at the Standard Model. It says photons, the particles of light, don't interact with the Higgs field at all, so they can't get any inertial mass from it. The only thing with mass is the box itself. So according to the Standard Model, the total inertial mass is still just 1 kilogram.
11 kilograms versus 1 kilogram. I mean, this isn't some tiny rounding error we can just sweep under the rug. This is a massive, fundamental contradiction between our two best theories of the universe. They just can't both be right. So what's going on?
Well, this huge problem has physicists scrambling, and it's forcing them to look at some really radical ideas. One of them actually brings us back to a concept that's over a century old, from a physicist named Ernst Mach, and it's a totally different way of looking at everything.
Mach's idea is summed up in this one incredible sentence. Mass out there influences inertia here. Just let that sink in for a second. What he's suggesting is that an object's inertia, that stubbornness, that resistance to being pushed, isn't some property it owns. It's not inside the object. It's a relationship between that object and, well, everything else in the entire universe. So here's the proposed solution, and it's a wild one. What if inertia isn't an intrinsic property at all? What if, when you push on something, that resistance you feel is actually the cumulative gravitational pull of every single star, every single galaxy, all the mass in the universe pulling back on it? If that were true, then gravitational mass and inertial mass would have the exact same origin, gravity itself. They'd have to be the same thing, and that would explain the equivalence principle perfectly without ever needing a Higgs field to begin with. And that leaves us with this just mind-bending final thought. We think of our mass as being ours, right? It's the most basic property that makes us, us. But what if it's not? What if that feeling of being solid, of having substance, is really just a constant, silent connection between you and the rest of the cosmos? It just goes to show you. Sometimes the simplest questions we can ask lead to the deepest and most beautiful mysteries of all.